Here's the next centripetal force video, and we're just going to do a couple of examples. And so let's see. This example is going to be a hill example. Let's just draw a hill, and we're going to draw the bottom of a hill. And let's imagine you're cruising by on your skateboard, and you're going to cruise down to the bottom of the hill down there. So there you are on your skateboard at the bottom of the hill. And let's say you've got a speed, and we'll make it really easy, 20 meters per second. You have a mass of 80 kilograms, and the question in this one is going to be, what's the normal force as you go down the hill? Now, you might have an intuitive sense that if you bottom out of the bottom of the hill, you kind of feel heavy. You feel this on a roller coaster. If you're in a car and you go down to the bottom of the hill, you feel heavier. So your normal force should be more than your weight if you're going to feel heavier, right? So let's figure this out. But one thing to notice is that we can approximate this part of the road as a circle, right? And then there's the center of the circle. So one other piece of information we're going to need to know is, what's the radius of this circle? So let's just call it 40 meters, right? So you can see it's not actually fully a circle, but right here when you're at the bottom of this path, you can approximate it as a circle. We'll just call the radius 40 meters. Okay, so once again, as in most force problems, start out by drawing a free body diagram. All right, there's you on your skateboard. What are the forces that are acting on you? Well, of course, you've got gravity going down. Let's just call that mg. You've got the normal force going up. We'll call that Fn. And that's it. Those are the forces that are acting on you. And then the way to start out, F net equals ma. Since this is a circular problem, let's talk about a for just briefly. What you might think of sometimes as acceleration is going to be changing your velocity. But in this case, the velocity is not going to change at all. What we're worried about here is that there's an acceleration because you're changing direction. Newton's first law says you'd rather just go straight this way, right? But you're not going to go straight this way. You're going to go around this circle right here. So this acceleration right here is not a change in speed, but it's a centripetal acceleration because you're going around in a circle. This is the circle that you're going around. That speed's going to stay the same. So it's not an acceleration speeding up or slowing down. It's going to be a centripetal acceleration, mv squared over r. Let's talk about the forces that are acting on you. Well, we still need to pick a direction as positive and a direction as negative. So let's just go ahead and say we'll pick up as positive and down as negative. Thinking about this, that's positive and then that's negative, so we can fill these in over here. And then we're going to have to make one adjustment. I think, no, we should be okay. So this is positive and that's negative. So this is going to turn out to be Fn minus mg equals mv squared over r. And we're looking for Fn. That's going to be Fn equals mv squared over r plus mg, right? Then we can just start plugging in some numbers. I'm going to drop the units for now because it gets a little bit messy. 80, that's the mass. 20 is the velocity squared, divided by 40, plus 80 is the mass. I'm just going to go ahead and use 10 for gravity. I know that some of you don't really like it when I do that, but that's just the way that it goes. All right. It just makes the math easier to do. So if we figure this part out, then this actually turns out to be 800 newtons, and this turns out to be 800 newtons. So the normal force is going to be 1600 newtons. Okay, let's do a comparison then. So we have 1600 newtons for the normal force. The weight, that's the weight right there, that's mg. The weight was 800 newtons, so you're going to feel twice as heavy. You're going to feel really heavy. how heavy you feel is actually not really dependent on your weight, but it's dependent on the normal force. If you have something pushing up on you with 1600 newtons, your brain thinks something else is pulling down on you with 1600 newtons. You're going to feel very, very heavy at the bottom of this ramp. Right? Let's do the counter example then. What if instead of going around a hill that way, what if you're going up and over like that? And here you are on your skateboard. Let's keep everything the same. Let's keep the speed the same, 20 meters per second. Right, we'll keep the mass the same. We'll keep the radius the same. Now this is going right here. Right, there's the radius of the circle. So for this part of the path, you're going around just a small part of a circle. Right, so let's see what's going to be different now. I'm going to draw a free body diagram. There's U. It's going to look exactly the same. There's the normal force. There's mg. Let's pick our up and down to be the same again. Let's pick up as positive and down as negative. We're going to write out a net force equation. F net equals ma, which of course we can write as mv squared over r. Here's something to realize though. This acceleration now, it's a centripetal acceleration. It's towards the center of the circle right here. And which direction is towards the center of the circle? Well, that's a negative direction, right? So this actually needs to be a negative value over here in order for everything to work out. So positive for Fn minus mg equals negative mv squared over r. That's going to turn into, the normal force is going to be mg minus mv squared over r. Using the same numbers that we had before, that's going to be 800 newtons minus 800 newtons equals 0. So that's no net force. So what are you going to feel? You're going to feel weightless. Now another science teacher actually calls weightless, instead of being called weightless, because you do actually have weight. Remember, there's your weight. That's mg. You do still weigh 800 newtons. What he calls weightless, he calls it no normal forceness. Right? If you don't have any normal force acting on you, you're not going to feel any weight. Coming back to the hill over here, you've been on a roller coaster, you've been over a bump in a car where all of a sudden it feels like your stomach's going into your chest and you feel funny. This is weightlessness right there, momentarily weightlessness. You actually still do weigh the same amount, it's just you don't have a normal force. Why don't you have a normal force? Well, if you think about what is necessary to go around a circle, Newton's first law says you want to keep going this way, and something's got to pull you to go around the circle. Some force has to take you this way. Well, the only force that can do that is gravity, and gravity is getting used up. All of gravity, all 800 newtons of gravity is getting used up to take you around the circle, and nothing's left over to actually, say, pull you down. Right? Gravity is pulling you down, but it's all being used to make you go around in a circle. Otherwise, you would just go flying off. And you can imagine if you increase the speed enough, you would go flying off. Gravity wouldn't be able to provide you with enough centripetal force to keep you held down, and you go flying off. And roller coaster designers have to think about this. How fast can the roller coaster go up over the top of the hill before people are going to be thrown out of the roller coaster? Assuming they have a seatbelt on, that might not be an issue. So just think about this. Normal force doesn't necessarily equal the weight. Here the normal force was 0. Back in this example, the normal force was twice as much as the weight. So don't get fooled that normal force always has to equal weight.